Let's continue talking about dummy variables in the context of multiple linear regression. So today we're going to be talking about a specific example, but before we get into that, let's try to summarize, some key ideas regarding dummy variables. So remember, dummy variables in the context of the multiple linear regression model. So, we started with the definition of a dummy or binary variable. So it's a variable that can take the values of 0 and 1. And, and this 0 and 1 represents qualitative information. So we use 0 and 1 to go from qualitative to quantitative information. I mean, the information contained in the DOM is still qualitative, but now we can use zeros and ones to run our regression model. So, for example, in a model where we only have one dummy variable as explanatory variable, we just write our model the same way that we wrote it before. We use the same procedures. And we can go and estimate our model. And then we said, okay, so now how do we about interpreting, these coefficients that we obtain when we get, when we use dummy variables? And to start the discussion, we say, okay, well, let's start with the case where we have one qualitative variable. So we talk about one qualitative variable. One qualitative variable that represents two groups. Yeah, with two categories. That's what I was talking about in the previous class. So we have one qualitative variable representing two categories. Okay, so we say, well, if that's the case, then, for interpretation purposes, we said that beta naught is the average value of y when delta is equal to 0. Okay, so that's the same as before. And we said that delta represents the difference between the average value of y when delta is equal to 1 and the average value of y when delta is equal to 0. Okay, so that's kind of what we talked about, the previous class. And today, we're going to be practicing how to use this information in the context of a specific example. Okay, so this is the example. So we have data from 526 individuals. It was used to analyze the effect of gender on wages. That's a discussion. It's even current discussion. Some people talk about the gender gap in wages. So we have the wage. We have potentially two dummy variables, one for female and one for male. So, the way to think about this problem is as follows. Let's say, if we think in terms of Excel, we say that we have gender, and here we have male, information about that individual. And I'm gonna, let's say, I. So it's the first individual, the second individual, third individual. So we have the gender. Okay, so what we can do, remember, our qualitative variable here, so gender is a qualitative variable. with two categories, which is male and female. So you can see here, that's what we have here in this column. And you see a qualitative variable with two categories. That means that we can create two dummy variables. We can create a dummy variable for each category. So for example, we could use a dummy variable for female. So if female is the dummy variable, that means that male is going to be equal to 0, male equal to 0, female 1, female, oh. Yeah, so that's correct. And for the male variable, we can create this alternative dummy variable where we have male is going to be equal to 1, female 0, and female 0. Okay? Again, so here the idea, we have this qualitative variable with two categories. So we can create two dummy variables. But we only include one in the model. Only one in the multiple linear regression model. And I'll go back to that idea. Okay, so this is what you have. This is the type of data that we have. So we have this model where we have wage, and the variable that was included was female. So remember, something that's important here is, if female is the variable that we have included, remember that the base category is going to be male, because remember, so if we have a female is equal to 1, but if we have a male, female is equal to 0. So that's why you see the base category is going to be male in this context. Okay, so let's see some more statistics. This is kind of a little bit data that's a little bit old. Average wage $5.9. Female, so you see the average for this female dummy variable is 0.47. So remember, this is the average of zeros and ones. Okay, so female is equal to 0.47. So that's the average for that variable. And actually, this value, this has a very intuitive interpretation. If female is equal to 0.47, that means that 47% of individuals, oops, I touched something. So that means that 47% of individuals in the sample are females. Okay, so very intuitive. The average value of a dummy variable represents the proportion of individuals for which that variable has a value equal to 1. In this case, the proportion of individuals that for which female is equal to 1 is going to be 47%. And you see, it kind of makes sense, because for males is 0.52. Well, this is almost, if we round it, it's going to be 0.48, so it's 48%. So that for male, the average is 0.52, which means that 52 of the individuals in the sample are males, which is kind of that what you would expect. And you see the sum of the average for female and male is equal to 1. That's what, we have our dummy variable. Okay, so you run the regression, and you have your regression, the results, regular results. This is a beta half coefficient, so this is beta 1 coefficient. So these are the coefficients. The standard errors, t-values, p-values. So is the model useful to explain wedges? Why? Just to practice. The statistics 68.53, and the p-value for f is less than 0.05. So the answer is yes. since the p-value for the F statistic is less than 0.05, so at the 5% level. So therefore, the model is useful for prediction. Okay, so is the female dummy variable statistically significant? Remember, we have to go and look at the p-values, and that p-value is less than 0.01. So at the 5% level, yes, of course, the p-value is less than 0.05, and yes too, because that p-value is less than 0.01. Again, what we're looking at here is this p-value that corresponds to that female dummy variable, and that's 0.00, which means that this is smaller than 0.01. So the next question, interpret the coefficient related to female. So let's write our estimated regression model. 0.099 minus 2.59 female. See, we go back here, so 7.0.99 and minus 2.512. So that's what we have. So this is our estimated model. So beta 1, which is the coefficient related to female, minus 2.59. So remember that theoretically, at the beginning of the class, that we say that that is basically, that represents the difference in the average value of wages for females relative to males. So for interpretation, we can always say that relative to the baseline category, which is males, the average wage for females is $2.512 per hour, and since that's a negative sign, we can say that's low. So again, and I go back to that kind of formula that I wrote for the interpretation of coefficient. So we always say relative to the baseline, and then we can say the average wage for females is $2.512 per hour lower. So what's the predicted average wage for males? It's very easy. So our estimated model, 0.099 minus 2.51. So for males, remember, female is equal to 0 for males, so we just plug in that value. So female is a 0 for males, which means that the predicted value is going to be 7.099. So that's the average wage for males. The predicted average wage for females. So remember, for females, female is going to be equal to 1. So we have to plug in our estimated model, and where we have, see, female here, that's what I'm doing. I'm using that equation at the top, times 1. So the wage is 5. It's gonna be 4.587 dollars per hour. Okay, so actually, if you see here, the difference between those two coefficients is 2.512. So the wage for females is 4.587, and the wedge for males is 7.099. So remember, that's the way that we interpret that coefficient 2.52, by saying that relative to males, which make on average 7.099, the average wedge for females, which make $4.587 on average, so that difference, and that delta, is 2.512, and that's kind of the way that we had interpreted previously. Okay, so that kind of confirms that the way that we're interpreting. So interpret the intercept. So remember, usually the way that we interpret the intercept, we say that that's the average value of y when x is equal to 0. So remember, in this case, x is equal to 0 means that female is equal to 0, which means that that's a male. Okay, so we interpret the intercept. So remember what we would have to write, and we already wrote that one, 0.99 minus 2.512, 0. So that's 7.99, which, you see, is the same as the average, the predicted average value for males. So in this case, the intercept represents the average wedge for males. Because remember, that is when female is equal to 0. Okay, so that has a very intuitive interpretation in this context. Okay, so now let's consider the other model. Now let's use male instead of female. So remember, if we basically what we're saying is male is equal to 1 if male, and male is equal to 0 if female. So female is the base category. Okay, for interpretation of the coefficients. So this is a regression output. So, for comparison purpose, let's compare the R-square of both models. So the R-square in this model is 0.116. Okay, let's go to the previous model. It's the same thing. So the next thing is depth statistics. So depth statistics here was 68.537. And in this model, depth statistics 68.537, so it's the same thing. Okay, so let's look at the test statistics. To do the test statistics, so let's look at the t-values for the coefficients. I'm gonna summarize here. So let's look at the model with female and the model with male. And let me see, of course, here in both cases we're going to have an intercept. In the model with female we will have female, and the model with male we have male. And notice that here what I'm trying to do is I'm trying to write the t-values for the coefficients. So the intercept 33.806 and female minus 8.279. For males 20.950. Here we don't have a coefficient. Here we don't have a coefficient. And this is going to be 8.279. So notice that the t-values are going to be different. So where did I get these ones? So this is the t-value here, and this is the t-value for male. Okay, so you can see that the t-values are different, but they are different because the coefficients represent different things. So you shouldn't be surprised about it. So they are different because those t-values are the t-values for different coefficients. Those coefficients represent different things. Okay? So let's interpret the coefficient related to male as before. So 2.512. 2.512. So again, the one corresponding to male means that the baseline is, the base category is female. So for interpretation, we can say that relative to female, okay, so we say that relative to females, the average waist for males is $2.51 higher. So the average wage for males is $2.51 higher. Okay? Of course, you see this coefficient is positive and the t-value is positive. Previously, that coefficient was negative and the t-value was negative. But in either case, they are both highly significant. So what's the predicted average wage for females? Again, we need to start with a model, the estimated model, 4.588 plus 2.512 male. So for females, remember, male is equal to 0. This is 4 pi plus 252 times 0, because for females, male is equal to 0. Okay? So you notice that this is basically the intercept. So the intercept, once again, represents the average value, the average wages for females. And the predicted average value for males, the wage equal to 4.58 plus 2.512 times 1. So for males, male is equal to 1. And that's what we've done here. And that gives us 7.110. Once again, if we want to see this difference, the delta between 4.588, should write it nicer. It should be 2.512. Okay, so if you see the predicted value for males, 7.1, for females, 4.88. So let's go to the previous model. For females, 4.587, well, I mean, it's a rounding error, and 7.099, so they're basically the same thing. So for males, 7.10, and for females, 4.59, which is exactly what, we got here, except for, some random error issue. Okay, so here the bottom line, remember the idea here, what we were trying to do is we are trying to estimate a model with a dummy variable that contains information, qualitative information about variable regarding two categories, The idea is, if that's the case, if you have one qualitative variable representing two categories, we can create two dummy variables, one for each category, but we only include one of them in the regression model. Ultimately, the content that we have, the information that we get back from that regression is exactly the same. It doesn't matter which of the regression models we use. Now, some of you might be wondering, okay, so why we can't include both variables in the regression model? And that's something that you can try to do. Let me see if I can find the file. And I'm going to show you. I tried to do that, so to show you what happens. You do that. Have the file open. Let me see. Cannot find the file. The problem is that let me see if I can get access to this file. Let me see if that gives me access to that file now. Oh. Okay, so I have the file here. Okay, so that's what I did. I tried to include both. You see here the Excel output. I tried to include both male and female in the model, but as you can see, I get an error for female. So actually, Excel recognizes that that's a problem, that they are both male and female. It's basically contained the same information. So Excel drops one of the variables. Excel drops one of the variables and only includes the other one. Okay, so you cannot estimate a model with both female and male because they are perfectly correlated. And actually, you see the problem there is that violates that no perfect collinearity assumption of multiple linear regression model. So it's kind of related to that condition. We cannot have them both. So that's kind of like a final note. You cannot you can't estimate a model with both male and female they are perfectly correlated. Thus, that violates the no perfect collinearity assumption. The no perfect collinearity assumption of multiple linear regression. Okay, so and with that, I think that we can cover this example about the use of dummy variable to represent qualitative information of two categories within the context of the multiple linear regression model.